In this video, we're going to look at a particular cryptography method called the Caesar shift cipher. Along the way, we'll find out a bit about the history of this technique and talk through some ways to approach decrypting messages that have been Caesar shifted by an unknown number of places. We'll even go through a bit of Python code that you can use for Caesar shifting your own secret messages. If you want to send a secret message to your friends or allies without other people knowing what you've written, then you need some kind of secure way of doing this. There are lots of situations where you might want to keep your message secret, but historically one of the situations which requires the secure transmission of messages has been war plans and military commands. Hundreds of years ago, the vast majority of the population couldn't read or write, so if you wrote down your message on a piece of paper and sent it, it was actually pretty unlikely that anyone would be able to intercept your message. As more people learned to read and write, military leaders developed ways of getting their clandestine messages to the front line. One way was to shave the head of a messenger, tattoo the message on their head and let their hair grow back, then send them to the front line, where their head could be shaved again and the message read. Obviously this isn't ideal for emergency messages, but it could be surprisingly effective for less urgent notes, as nobody would suspect the messenger was carrying a secret message under their hair. Another technique involved writing a sequence of letters on a belt or a strip of parchment, which could be wrapped around a pole of a certain diameter, so that the letters in the message lined up alongside each other. The pole was called a skytail, and you can try this technique yourself with a thin strip of paper and a pencil. Just wrap the strip of paper around your pencil in a spiral and write your short message on one side, then fill in the gaps with random letters and unravel it. Now the strip contains a random jumble of letters, but when you wrap it around your pencil, you can read your message clearly. Now this is neat, but if the enemy discovered a strip of parchment with a string of apparently random letters on it, they would strongly suspect it contained a secret message and can just wrap it around a range of poles of different diameters until a message appeared in front of their eyes. Or they could just look at every fourth or fifth or sixth letter in a regular pattern. It wasn't massively secure. So no matter how you try to hide a message, if you just write it down in plain text and the enemy discovers it, they can just read what you were saying. A better idea is to use a secret system to change the letters so that the enemy won't be able to understand what you've written if they discover it. There are loads of ways of doing this, but one simple way is called the Caesar shift cipher, named after the Roman politician and military general Julius Caesar, who apparently was fond of using it for his messages. These days, it's a pretty easy code to crack, but back when much of the population couldn't read or write, it was probably quite effective. Even for those who could read, if they saw a bunch of random letters on a piece of paper like this, they'd assume it was in a different language, and they wouldn't know how to decode it. Here's how the Caesar shift cipher works. You simply shift each letter in your message a bit further down the alphabet and rewrite the message using the later letters. Apparently, Julius Caesar used a shift size of 3, so when he wanted to use the letter A, he would replace it with the letter D. If he wanted to use the letter B, he would replace it with the letter E, and so on. And when you get to the end of the alphabet, you can just wrap the letters around. So V becomes Y, W becomes Z, then X becomes A, Y becomes B, and Z becomes C. In this way, if we wanted to write the message attack at midday, we could write out the alphabet and then write it out again below with all the letters shifted 3 to the left. Then A is written as D, T as W, C as F, K as N, M as P, I as L, D as G, and Y as B. So the message we send would be DWWDFN DWPLGGDB. It's quite surprising how confusing this makes your message look. If you didn't know about the method used to encode the message, it wouldn't be at all obvious what the message was saying. Anyway, the commander in the front line would receive this message and would write out the alphabet again, this time with all the letters shifted 3 places to the right, and they could decode the message. The D in the message would have come from A originally, the W would have been a T, the F would have been a C, the N would have been a K, and so on. Of course, if you always shifted the alphabet by 3 places, eventually the enemy would be able to work out your system. For example, there are 2 instances of the same letter being used twice in a row in our attack at midday message, 2 T's and 2 D's. Now, not all letters can be used twice in a row in the middle of words in English, and a few are much more likely than others to appear that way. So you could eliminate some possibilities. Also, there's a 2-letter word in the message, and there aren't that many 2-letter words in English. If you had 1-letter words, then there are even fewer of those. So over the course of several messages, you could start to work out which letters were being replaced by which other ones. So another approach would be to shift each message by a different number of places. For example, one day you might shift 9 places and attack at midday would become JCC JLT JCVR MMJH, and another day you might shift 21 places to get VOO VXF VO HD YYVT. This would make the enemy's task much harder, and so long as your frontline commander knew how many places to shift on a particular day, then they could easily decode the message. If, however, your enemy realised that you were doing Caesar shifts of different amounts each day, then it's not a massive task to try all of the possible shifts to decode your message. This is called the total enumeration approach. There are 26 letters in the alphabet, so there's only 25 ways to do a Caesar shift. You can shift 1, 2, 3, 4, up to 25 places. If you shift 26 places, then A would map onto A, B would map onto B, C would map onto C, and so on. And that wouldn't really be a very secret message. So we don't do a shift of 26 places. Now, shifting 27 places is just like shifting 1 place, and shifting 28 places is just like shifting 2 places, and so on. It's like modular arithmetic. If we shift n places, where n is bigger than 25, then actually it ends up looping round, and the number of places we shift is equal to the remainder we get when dividing n by 26. So, to try all possible shifts, we just need to try shifts of 1 to 25 places. Another slightly more analytical approach would be to do some letter frequency analysis. The idea is that you can count letter frequencies in large samples of text from a language, for example in literature, dictionaries, or these days websites and online articles. From this you can work out the order of relative frequencies of letters. You can then count up the number of each letter used in your encrypted message, and the most common letter is likely to be the most commonly used letter in that language, and the least common letter is likely to be the least commonly used letter in that language. This gives you a good starting point for working out how many places the letters in your message have been shifted. This can go a bit wrong, of course, if the encrypted message is not a representative sample of the English language. For example, if the message is about Zach's zany zither playing pizzazz on the piazza while eating pizza, it will contain an uncharacteristically large number of Zs. So you could go one stage further and calculate the Spearman's rank correlation coefficients between the rankings of all letter frequencies in the English language and the letters in the encrypted message when shifted 1 to 25 places. The shift size with the strongest positive correlation tells you about the shift size that was most likely to have been used in encrypting the message. You do need to think a little bit carefully about which way the shift is happening though. Remember that the original message is shifted forwards a certain number of places, so the decryption needs to shift letters backwards that number of places. But because letters move around in a loop and the shift sizes behave in a modular way, you can express a given shift in 2 different equivalent ways. For example, Julius Caesar's favourite 3-character shift forward is the same as a 23-character shift backwards. Shifting all the letters in the alphabet 3 places to the right gives us the same code as shifting them all 23 places to the left. And this helps us think about another way of coding and decoding messages. If you've got a message that was encoded using a forward shift of 3 places, then you can either shift it backwards 3 places to decode it, or shift it forward another 26 minus 3. That's 23 places, bringing it up to a grand total of 26 places shifted. That's right back to where it started, exactly once round the alphabet loop. So in general, a forward shift of n places is equivalent to a backward shift of 26 minus n places. And to decode a message that was coded using a shift of n places, you need to shift it forward another 26 minus n places. Now, there are many other ways of encrypting messages, and we're not going to talk about them here in any detail, but I'm sure you can imagine that an encryption method such as the Caesar shift cipher that always substitutes each letter with a consistent other letter is quite a weak encryption algorithm which can easily be cracked by total enumeration or letter frequency analysis. The Enigma machines used by the Germans in the Second World War, for example, were much more sophisticated because they used a system of dials that would change the way letters were mapped each time you pressed a key. There were several variants of the machine, but at their heart, they still used a simple substitution cipher. However, with the type used by the Army and Air Force for much of the war, they chose 3 rotors from 5 available, used one of 26 possible initial rotor settings for each, connected 10 pairs of letters on the plug board, and the rotors moved after each key press, so that instead of there only being 25 possible variations to try in a total enumeration approach to decoding the message, there were nearly 160 quadrillion, Also, because letter mappings changed for each character in the message, letter frequency analysis on encoded messages was useless, so decoding the messages was a much more complex task. Now, before we go, let's take a look at how you can write a little Python computer program to encode your own messages using the Caesar shift cipher. So here, you enter the number of places you'd like to shift, so how many letters down the alphabet you like your letters to move. And here, you type in the message you'd like to encode. This bit just initializes the output message to be nothing at all, so they're just two single quotes. Then the main part of the program is this big loop here. It's looping through each character in the text message that you input, and it's finding the ASCII code value for each of the characters. Then, if it's a letter between uppercase A and uppercase Z, then it'll add the shift size that you mentioned earlier to that ASCII code. So the letter A becomes B, for example, and B becomes C, and so on, if you had a shift size of 1. Then, if that shift took you off the end of the alphabet, this bit of code here would take away 26 from the ASCII code and loop you back round the alphabet. This line here just adds that shifted character to the end of your new message, and then it goes back round the loop again until it's gone all the way through your input message, and the encoded message will be in this variable here called shifted text. Then finally, it prints out your shifted text. Now, this program doesn't do any error checking or validation, and you'll need to type in your original message in uppercase letters only, but it's a start, and you can take this code and improve it if you like. Using the information we've talked about in this video, you should be able to use that program to encode and decode messages using Caesar shift ciphers of any amount. Remember, if the message is encoded using a shift of n places, then you can decode it by shifting the encoded message 26 minus n places. KYREBJ, WFI, NRKTYZEX, REU, YRGGP, TFUV-SIVRBZEX, VMV, IPFEV. When you subscribe to our channel, remember to click the bell to ensure you get notifications about our new videos. And for more mathematics content, why not follow the link in the description below to nagwa.com.